Now let's introduce direct and alternating current, two different types of current. And we'll talk about power transmission after that. So current can flow two different ways. The way you've probably been thinking of current so far is direct current. So if we're talking about the electrons exit at or move from the low potential or low voltage side of a wire to the high voltage side, and they just move again, kind of like a train, all together, moving through the wire in the same direction at relatively the same speed. Remember, these electrons are bouncing off things, so not moving at exactly the same speed, but generally moving in the same direction. That's opposed to an alternating current, where the current is actually increasing and decreasing with time. And more than just increasing, decreasing, it's not just pulsating, but it's oscillating. It's going from positive to negative, meaning one moment the electrons are moving forward, and then they're moving back, and then they're moving forward, and then they're moving back. You can see it in these graphs, right? The current for DC is continuous, constant at the same value throughout time. Whereas for alternating, it goes positive and negative and positive and negative. And if you remember when we talked about waves, the medium doesn't actually move, right? So when you're looking at sound waves, the atoms in air don't actually propagate with the sound wave. Water, when you look at water waves, the water doesn't propagate with the wave. Sorry, with the energy. It's the energy that's propagating, not the medium. So we have the same thing here with alternating currents. Electrons aren't actually really getting anywhere. They're moving a bit forward, but then moving a bit back, and then a bit forward, and then a bit back. So there's no net displacement. And again, it's the energy that's moving forward. Or that's being propagated. And again, at the end of the day, that's all we care about is the energy. Now, there's times where DC current is more useful and times where AC current is more useful. And so because of that, we'll talk more about this a little bit later, but AC currents are generally used to transport or for power transmission, right? When power, let's say, is leaving power plants, we generally up it to a very high voltage for that transmission because we lose less energy when power is transmitted at high voltage, and we need AC in order to do that. You can't change the voltage of DC power as easily. And then, of course, before that power gets into your home, we need to step it down to a more usable and safe voltage level. So again, we'll come back to that. Now, how do you get an alternating current? Well, you need something that changes essentially that switches the sign of charges on, say, like on a battery, right? So if you imagine taking a battery and quickly flipping it back and forth, that could give you an AC current. Now, of course, you can't really do that with an actual battery in some normal circuit. Instead, you use a generator or an alternator that switches the sign of the charge periodically. So one moment it's propelling the electrons forward and then back and then forward and then back, again with no net displacement. Commercial electricity in North America sticks to volts or 120 volts. However, the higher the voltage, the less energy that's lost, the more efficient the current. So in Europe, they stick to the 220 volts as their standard, not 120. The U.S. stuck to 120 essentially because it had already been used for so long, and it would have taken a lot to transition. So we just stuck to the 120. How do you convert from one to the other? We need to be able to turn AC current into DC current, because most of your electronics at home use DC, right? Your laptop needs DC power, your toaster needs DC power, but the power you get from an outlet is AC. It's alternating. So we use what's called a diode, this small electrical device, and it's essentially a one-way path for these electrons. So even if we have alternating current coming in, it'll only allow current in one direction to go through. And it does this by slowly charging and discharging a capacitor, so that there's no point where we don't have any forward moving current. We end up with a pulsating current. So the current is DC, it's consistently forward moving in one direction, but it can increase slightly in strength and drop in strength, as opposed to completely flipping direction. So let's look at some misconceptions. One is that, quote, current is propagated through the conducting wires by electrons bumping into one another. That is not true, right? I used an analogy of a train before, but in this sense, it's not true, right? One electron doesn't push the electron in front of it, and the electron in front of it. The electrons are moving because of the electric field. So it's the same way as if I took a whole bunch of balls and held them up and let go, they're not going to push each other. It's gravity that's pushing all of them down. So similarly, in a wire, the electric field is what's pushing electrons through the conductor. They are colliding and bouncing off each other, but that's not what's causing them to move, right? So the electric field propels them forward, but as they do that, they'll hit an atom, which might bounce them backwards or bounce them upwards. So they have this sort of random motion still, and this random motion is essentially simultaneous with their forward motion that's given to them by the electric field. So they bounce around, but overall have a forward propagation. And so it turns out that the current, although the electrons move at very slow speeds, we said before at about 1 millimeter per second, the current is established through the wire at close to the speed of light. But again, it's not the electrons moving at the speed of light. The electrons are already spread out throughout the wire. It's this electric field that's traveling close to the speed of light. The electric field extends throughout the wire at close to the speed of light. Another misconception: electrical outlets in the walls of homes are the source of electrons. Remember that our outlets provide AC power, and AC power does not actually move electrons. We don't have any net displacement, so we're not getting electrons out of an outlet. Rather, it's the energy that's being carried through. The energy comes out of the outlet and into your lamp or your toaster or your laptop or whatever it is that you are using. So the alternating current, these oscillating electrons, propagate energy from a power station to your outlet, and then that energy is converted into DC power, which is that energy is taken to run to power DC current, and that's used to power your equipment. So how do we know what the power of some current is? Remember that power is a measurement of energy per time, right? So joules per second, or in other words, watts. So power is given by current times voltage. Remember that voltage is energy per charge, right? So the more voltage you provide to a circuit, the more energy you can give to the charges. Lower voltage will give us less energy. Higher voltage will give us more energy per charge. So voltage is joules per charge. Current is charge per second. So when you multiply those units, the charges cancel, and you're left with joules per second, which is energy in watts. Let's talk a bit about different types of light bulbs. Incandescent bulbs are the least efficient light sources out there. They lose a lot of energy due to heat. You've likely noticed this if you have an incandescent bulb and you get too close to it, it gets quite warm and really hot. And these bulbs aren't meant to be heating you, right? These aren't heat lamps. They're meant to light up a room. So any heat that you feel, that's wasted energy, right? That's not what it's meant to be used for. And so fluorescent lamps are much more efficient. They emit much less heat. Again, you can test this. You'd feel less heat with putting your hand near a fluorescent bulb than you would an average incandescent bulb. And so by putting out less heat, that means more of that energy is actually going into light, into what you actually want to use the lamp or the bulb for. So fluorescent lamps have been turned into, or we have now compact fluorescent lamps, CFLs, which are fluorescent lamps that fit into a standard light bulb socket. And again, they are much more efficient than an incandescent bulb. They'll save you money if you use them. Another type of light source is a diode, right? A light emitting diode. This is basically the little red light you see, say on like on your stereo, that tells you whether it's on or off. It just flashes on red or off. These are also very efficient, and we also make light bulbs out of LEDs now as well. And they're a lot more useful and efficient than incandescent bulbs are.